As useful as our Bohr picture of the hydrogen atom is, there are some fundamental problems with it. For one thing, it doesn't work for anything other than hydrogen. So if we have a larger atom with more protons and neutrons and electrons, then our Bohr picture can't tell us what these energies are. Even for hydrogen, it fails to fully describe the atom. So for example, for the spectral series of hydrogen, where the lines where hydrogen absorbs and emits light, some of these lines are missing in the Bohr picture. It's not capable of predicting all of them. Well, the solution to this comes in 1926 from Erwin Schrodinger, and he comes up with a wave equation for this hydrogen electron, and this wave equation describes all of the properties it's possible to know about this electron. And so it's capable of predicting the full spectral series. The wave equation, you square the wave equation, that gives you the probability of finding the electron at a particular location and time. And the way this compares to our Bohr orbits, for example, the first Bohr orbit corresponds to this kind of peak here in our wave equation. And so there's a very high probability of observing the electron where that Bohr orbit was placed. But if scientists had had higher resolution instruments, they would have noticed that the electron would frequently be a little bit displaced, or infrequently very far displaced, from where that orbit was. Now, if we solve this equation, it doesn't just give us the Bohr orbits, it gives us some other solutions as well. The Bohr orbits are the ones that look kind of spherical, but there are other orbits with different shapes, and solving these gives the missing energies for our emission lines. And we can represent these solutions using 3 quantum numbers. And we'll also tack on a 4th quantum number to represent the electron which is occupying that orbital. So these are a number of those wave function solutions. Now this is the actual equation, and you can see it's a very complicated equation. We are fortunate, however, though, that this equation can be broken into pieces, and each of those pieces corresponds to a quantum number. And if we specify those quantum numbers, then we can specify which solution we are talking about. So here are some of the wave function solutions. For example, here are some that correspond to the Bohr orbits, these spherical solutions. And for these, we just have one quantum number, and the other quantum numbers are all 0. And as they vary, though, then we get these more interesting complex solutions which have different energies, and these were the ones which were omitted from the Bohr model. And it's very handy that we can just use these 3 numbers to describe our orbital and not have to use this entire equation here. So this is how that's going to work. The first number is the principal quantum number, n. So that's what Bohr knew about. And this describes the overall energy of the orbitals. This is frequently referred to as the electron shell, where all of these energies for a particular n value coincide. And n can be any positive integer. So we start counting at 1 and we go up, and in principle all are accessible. We can have n all the way up to infinity. Once we've chosen n, we can choose another quantum number called the angular momentum quantum number. And what this quantum number does is it describes the shape of the orbitals of our subshell. This can be any integer ranging all the way from 0 up to 1 less than n. So if n was equal to 3, then L could be 0, 1, or 2. And these are some of the shapes that L can give us. And so if L equals 0, then we get these spherical shapes, which correspond to the Bohr solutions. If we have L equals 1, we get kind of this double lobe shape. So here where our L value is. we have L equals 2, we get these quadruple lobes. And L equals 3, we get these maybe sextuple lobes. And there are some variations in these shapes, but this is generally how I will represent them, is with these 4 different pictures. And just like with n, in principle, L can range up all the way up to infinity. But for the most part, we're going to restrict ourselves to these shapes, which account for most of the elements in the periodic table. We can also tack on one last quantum number called the magnetic quantum number. The magnetic quantum number describes the orientation of this orbital, so which direction it's pointed. And this can be any integer in a range from negative L all the way up to positive L. So if we had this solution here, these d orbitals where L equals 2, then we could have L be equal to -2, -1, 0, 1, or 2. So for example, for the p orbitals, where L equals 1, it's what we set up here, then m sub L could be -1, 0, or +1. So that corresponds to 3 different orientations of those double-lobed p orbitals. And you could think of this as one being oriented along the x-axis, and one being oriented along the y-axis, and one being oriented along the z-axis. Those preceding 3 quantum numbers specify all the properties of one of those orbitals. Now within the orbital, we are placing the electron, and we need one more quantum number to describe the electron being placed inside of that orbital. The orientation of the electron is kind of weird here. It can be either up or down. Up corresponds to a quantum number of 1/2, and down corresponds to a quantum number of -1/2. You might think of this as a spinning top. It could be spinning clockwise or counterclockwise, but the top is not going to tilt over on its side as long as it's spinning really fast. These are going to be the only 2 possible values for its relative motion and position. Now, the spin quantum numbers is not really the same thing. It's actually something that we don't experience in everyday life, and so it doesn't have a classical analogy. But this might give you kind of a picture of something that has some similar properties, at least. Now let's consider an example of applying these quantum numbers. We might ask how many solutions to our hydrogen wave function correspond to the energy level where n equals 2. And for example, this would let us predict many of our spectral lines, being able to answer this question. Well, if we follow our rules, once we've chosen the n equals 2, then L will be allowed any values up to 2 minus 1, starting from 0, so it can be either 0 or 1. Now, m sub L can range from minus L to positive L, so if L is equal to 0, m sub L doesn't have a lot of options. It can just range up to 0. Now, if L is equal to 1, then we can range from minus 1 up to positive 1. So in that case, we can be minus 1, 0, or positive 1. So there are 3 solutions in that case. Now, in each of these orbitals, we can stick an electron, and our electron can always either be spin down or spin up. So there are going to be 2 possibilities for each of these. So for L equals 0, where ml equals 0 and ms equals plus or minus 1/2, there would be 1 times 1 times 2 is 2 possible configurations. And then for L equals 1, where we have 3 m sub L values, and again 2 m sub S values, there would be 1 times 3 times 2 is equal to 8 possibilities. And here's a listing of all those possibilities, where we have ml equal to minus 1, ml equal to 0, ml equal to plus 1, and then the different spin configurations for our electron. A very important rule which applies to our electrons that we're modeling is what's called the Pauli exclusion principle. The Pauli exclusion principle states that no two fermions, fermion is any particle with non-integer spin, for example our electrons with plus 1/2 and minus 1/2 spin, can have the same quantum numbers. So once we stick 2 electrons in our orbitals, one with spin up and one with spin down, then we're going to have to move on to some other orbital. We can't fit any more electrons in that, because otherwise we would be using electrons with identical quantum numbers, i.e. identical solutions to the Schrodinger wave equation. This becomes very important when we consider multi-electron atoms, so larger atoms in a periodic table. Now the results that we've come up with, they only apply to hydrogen with 1 electron. And it becomes very difficult to solve that Schrodinger wave equation for anything other than hydrogen. However, we are in luck because our solutions, even though they only apply to hydrogen, they're still reasonable approximations for our multi-electron atoms. And the reason they're good approximations is because the Pauli exclusion principle and electric repulsion keep these electrons out of each other's orbitals. So they tend to stick in their own orbitals, largely. And the only catch there is that the energies of these orbitals are going to be shifted. So, for example, hydrogen, the energies of those s orbitals and p orbitals and d orbitals and f orbitals for a particular n value is all the same. But now that we have these larger atoms, there's actually going to be a change. These s electrons are going to block part of the p orbital, just a little bit of it, but enough to shift its energy up. And same thing for the d orbitals and the f orbitals. So now there's actually an increasing hierarchy of energy for these different shapes for our orbitals. All right, now here's the grand finale to all of that. Just by being able to list those solutions to the Schrodinger wave equation, even though they're only approximations for multi-electron atoms, we're able to reconstruct the entire periodic table. Now, our periodic table, we're going to assume that all of our elements are in their ground state. That means they're in the lowest energy configuration. It's not a requirement. We could certainly, for example, stick the hydrogen electron in some higher energy orbital. But over time, physical systems tend to minimize their energy. And so that electron would decay back down to the lowest energy configuration and be back in the ground state. So we're just going to assume for the periodic table that everything's in its lowest energy configuration. So that's where we're going to start filling up our electrons. Now, our principal quantum number gives the overall energy level, or the shell, for the electrons. We start at n equals 1, and we count our way up. And it turns out that each of these is going to correspond to a row of the periodic table. So, for example, we start where n equals 1. Now, L can range all the way up to n minus 1. So in this case, the only possibility is 0. M sub L can range between minus L and positive L. So that's also going to be forced to be 0 in this case. And we have two values for M sub S, plus 1/2 and minus 1/2. So that gives us two possibilities. And that's why we have a width of 2 for this group over here in the periodic table. And here I've moved the helium over to the left side of the periodic table because it makes more sense in this case. You'll see periodic tables with helium on the left, or some move it over on the right because it behaves as a noble gas. Now that we have filled up that orbital, we can move on to the next shell where n equals 2. And here we have two possibilities for L. L can be 0 or 1. It ranges up to n minus 1. Now if it's 0, then m sub L again will be 0, and m sub S will be plus 1/2 or minus 1/2. So we have two possibilities. Now if we move over to where L equals 1, then m sub L can be minus 1, 0, or plus 1. And each of those has either ms is plus 1/2 or ms equals minus 1/2. So we'll have a total of 6 possibilities. So this explains the width here of this p block. It has a width of 6 elements. And that corresponds to each of these 3 ml solutions times 2 ms possibilities. And now once we go down to our next row, we now have a new possibility for L. L can be equal to 2. And so we have m sub L equal to minus 2, minus 1, minus 1, 0, 1, 2, and then our 2 m sub S possibilities. So 5 times 2 is 10, which gives us the width of this block. So this explains the entire structure of our periodic table. So that's pretty cool that we are able to predict this using our very simplified version of the Schrodinger wave equation. It's also pretty amazing that we were able to get this table long before we ever were able to solve the Schrodinger wave equation or even knew that it existed or might exist, based on our categorization of similarities between the elements. Now, why are there those similarities between the elements? We can now answer that question as well. In general, it's going to be the outer electrons which do the most interacting, which means that all the elements that have outer electrons with similar shaped orbitals, and especially if they have similar filling of the orbitals, are going to have similar chemical properties. And so that's why for any individual group in the periodic table, if you go down that group, in general, you tend to find similar characteristics. Because if, for example, we consider the alkali metals or the alkaline earth metals, their outer electrons are all in these s orbitals, which are similarly shaped. And for the alkali metals, that s orbital is half filled. For the alkaline earth metals, it's fully filled. And that accounts for their strong similarities in chemical behavior.